Hello, this is not your chem tutor, and this video is part 4 of our series on balancing nuclear reactions. In this video, we will talk about alpha decay. But before you continue this video, make sure you have watched part 3 of the series. There I talked about the different types of nuclear reactions, and alpha decay is one of the types of nuclear reactions. If you still haven't watched part 3, then don't worry, I will put the link in the description box. Again, as usual, in this video, I put several examples so we can do some practice. Okay, without further ado, let's proceed to the lesson. So let's just have a quick recap. As we have previously discussed, the alpha particle can be represented in two ways. It can be written using the Greek letter alpha or the elemental symbol for helium, which is He. For alpha particle, the atomic number is 2 and the mass number is 4. So that's your alpha particle. When we say alpha decay, it is when a nuclide emits or gives off an alpha particle. So as you can see in the screen, this is an example of an alpha decay. Specifically, this is the alpha decay of plutonium-239. So as you can see in the screen, in the equation, plutonium-239 emits or gives off an alpha particle. So you can see an alpha particle on the right side of the equation. So now that you are refreshed about alpha decay, let's move on to balancing alpha decay equations. First, let me teach you about the rules in balancing nuclear equations. So please take note that these rules apply in any types of nuclear reactions, whether it's alpha decay, beta decay, positron decay, etc. Okay? So there are only two rules you need to familiarize. The first one, you must balance the mass number. So this means that the sum of the mass numbers of the reactants must be equal to the sum of the mass numbers of the products. The second rule, you must balance the atomic number. That is, the sum of the atomic numbers of the reactants must be equal to the sum of the atomic numbers of the products. So these are actually simple rules. Now let's apply it into our examples to see if these nuclear equations are balanced or not. So let's try the first one. First rule, balance the mass number. So on the left side, the mass number is 239. On the right side, the total mass number is 235 plus 4, that is 239. So the left side and the right side are the same, so that means the mass number is balanced. Now let's try the second rule, balanced atomic number. So on the left side, the atomic number is 94. And on the right side, the total atomic number is 92 plus 2. That's a total of 94. So the left side and the right side have equal numbers. So that means the atomic number is also balanced. Since the equation satisfies the first and the second rule, that means this is balanced. Let's try our second example. On the left side, the mass number is 235. On the right side, the total mass number is 231 plus 4. That means it's 235 in total. So mass number is balanced. For atomic number, on the left side, we have 92. On the right side, we have 90 plus 2. That's a total of 92. So atomic number is also balanced. So that means the second equation is also balanced. So that's how you know that the equation is balanced or not. Okay, since you already know the rules, let's do some exercises. Okay, so for this exercise, we need to balance the following alpha decay equations by filling in the blanks. So for each equation, we will identify the missing daughter nucleus. So please grab your periodic table. We will need it to solve this exercise. So do you have your periodic tables with you? Okay. So let's try the first one. Just remember the two rules in balancing nuclear equations. The atomic number must be balanced, the mass number must be balanced. So for the first one, on the left side, the atomic number is 78. On the right side, the atomic number is 2 plus blank. So what should you put in the blank to match the right side and the left side? So you put 76. Because 2 plus 76 is 78. Okay? And you know that this number is the atomic number of the element. So what is the 76th element in the periodic table? That's osmium or OS. Now let's balance the mass number. On the left side, we have 175. On the right side, we have 4 plus blank. So what should you put in the blank? Obviously, it's 171. Because 171 plus 4 is 175. So the answer for the first one is osmium 171. So let's try the second one. On the left side, the atomic number is 84. On the right side, we have 2 plus blank. So what should we put on the blank? We put 82 because 82 plus 2 is 84. So what is the 82nd element in the periodic table? That would be lead or Pb. Let's balance the mass number. On the left side, we have 208. On the right side, we have 4. So what should we put in the blank? We should put 204 because 204 plus 4 is 208. So the answer for the second one is lead 204. Now let's proceed to the third example. Okay, this time the blank is on the left side. So we will identify the parent nucleus in the alpha decay equation. Okay, so just remember the two rules: balance atomic number, balance mass number. So for the third example, on the right side, the total is 2 plus 86. That is 88. So therefore, the atomic number on the left side must also be 88. And what is the 88th element in the periodic table? That would be Ra or radium. How about the mass number? So on the right side, we have 4 plus 222. That's 226. So on the left side, you also put 226 to balance. So the answer is radium 226. And finally, for our last example, so for the right side, we have 2 plus 90. That's 92. So to balance, we also put 92 on the left side. And what is the 92nd element? That is uranium. And for the mass number, we have on the right side 4 plus 230. That's 234. So to balance, you should put 234 on the left side. So the answer is uranium 234. Okay, so I hope you've been following, and I hope you understood how to balance alpha decay equations. So for our second exercise, It says here, write the balanced alpha decay equations for the following nuclides. So here we are given parent nuclides, and we will write the alpha decay equations for each. Okay, so first one, we have gold 185. So remember, alpha decay, the parent nuclide gives off an alpha particle. So it gives off an alpha particle. So alpha particle, you know the symbol, that's He24 plus blank. We need to identify the daughter nucleus. So let's use the rules in balancing. On the left side, we have 79 as the atomic number. On the right side, we have 2 plus blank. So of course, that's 77. Because 77 plus 2 is 79. So what is the 77th element in the periodic table? That would be IR, or iridium. So let's balance the mass number. On the left side, we have 185. On the right side, we have 4 plus blank. That should be 181, because 181 plus 4 is 185. So let's just rewrite the balance equation. That's gold 185, and it decays into the alpha particle plus iridium 181. So this is the answer to the first part. For the second part, we need to write the alpha decay of francium 221. So francium 221 gives off, of course, an alpha particle, He24 plus blank. So what should be the daughter nucleus? So we need to use the rules in balancing. On the left side, it's 87. On the right side, 2 plus blank. So that's 85. Because 85 plus 2 is 87. So what is the 85th element in the periodic table? That's astatine, AT. For the mass number, on the left side, we have 221. On the right side, we have 4. So what should be 4 plus blank? It should be 217. Because 217 plus 4 is 221. So let's just rewrite the balanced equation. So that's francium 221. It decays into an alpha particle plus astatine 217. So this is the answer to the second part.